Chemical, this is chapter 4 in the lecture outline, and this is referred to as chemical stoichiometry. Or the mathematics, or applying mathematics to the problems of chemistry. Some of the things that I'm about to start with you've had before, and it should be no problem. But I give this so that it blends naturally into what we call the king of chemistry, the mole concept. And I'm not going to go into all the stuff about animals and stuff. That's something else. So mole is a mass number. So we'll get there. Okay. First thing we want to look at is, well, let me tell you how it's going to come together. We're going to start with atoms and elements, then go to molecules, compounds, then reactions. So as I make this presentation, kind of keep that little listed focus in the back of your mind so that you know kind of understand why I'm doing certain things at certain points in the presentation. So in terms of atoms and elements, we want to start with molecular weight. And sometimes I'll list this as formula weight. F weight. You'll see me write it in that context many times. And it means it's the molecular weight or the formula weight that is given. And it's obviously the sum of all the atomic weights gives the formula weight or molecular weight. And this is easy to understand. H2O, for example, is 2 hydrogens plus oxygen. I like to round to the whole number because if there's any digits past the decimal needed, just look at your answer choices or whatever the circumstances in the lab present. You work your decimal inaccuracy from that standpoint. So it's 2 times 1 plus 16. And typically these are listed in AMU terms before I get to this chapter. And it's called atomic mass units. And so that is equal to 18 AMU. Or it might be listed 18 gram formula weights per formula weight, or grams per formula weights, what I should say, like that. And so I think you have seen this in the past and shouldn't have any trouble with it. KClO3 formula weight, potassium plus chloride plus 3 oxygens, that's I think it's 39 plus 35 plus 3 times 16 and grams per formula weight. And so you get an idea of what we've done. So I am going to move forward in the next level because I'm assuming y'all can manage this. You want me to do some more, let me know. If you're shy about it, send me a note and I'll give you some worksheets on it. But you'll have many opportunities to deal with the formula weight. You'll understand why as we get deeper. In chemistry, what does a mole mean? 1 mole is a mass number. Mole is to formula weights and so forth as tons is to pounds, like 2,000 pounds is a ton kind of thing. Well, there is a number standard that relates to moles, and that is 1 mole, by definition, is the mass of substance containing 1 Avogadro's number of particles. A mole applies to elements and compounds. There is 1 mole of oxygen gas, or 1 mole of argon gas. This both is the application. And what it means is 1 mole of O2, if I had it in my hand or in a bottle, would be 6.02 times 10 to the 23rd molecules of O2 gas. If I'm talking about 1 mole of argon gas, then we would be speaking of 6.02 times 10 to the 23rd atoms of argon gas, to give you an example. Now, it's also the formula weight. The mass of substance that contains the Avogadro numbers is equal to the formula weight. So 1 mole, which is 1 Avogadro's number, this is the abbreviation for it, or symbology for it, a capital N with a subscript 0, is also 1 formula weight of substance. That is 1 mole, we're talking about O2, is 2 times 16 grams. And we call that grams per mole, and that's 32 grams per mole. So the formula weight is also a mole. 1 mole argon, we look up on the periodic chart, 1 mole of it, 40. And we tag that with grams per mole, like that. So what I want to orient you with is this relationship right here first. 1 mole is the mass of substance containing 1 Avogadro's number of particles and is a formula weight. So when you are calculating moles of a substance, it will be that fraction of Avogadro's number if it's not 1 full Avogadro's number. So we move. Now what you're going to run up against is this. Converting from moles to grams and grams back to moles. We'll start with grams. And then moles back to grams. Well, it's a real simple process. The number of moles is equal to the given mass divided by the formula weight. That's it. And you tag it with the unit moles. Given 63 grams of HCl. that has a formula weight equal to 36 grams per mole. That's 35 and 1. Yes? Everybody kind of that? 35 times 1. You're 36. So if we're given 63 grams, number of moles of HCl is equal to the mass, 63 grams, over 36 grams per mole. And you can see how the units will invert, multiply, and grams will cancel in that calculation. And that gives us a 1.75 mole of HCl. And that's the simplicity of it. Converting moles to grams you multiply times formula weight. That is, grams is equal to moles, or given moles, times formula weight. Given 0.00287 mole of O2 gas equals how many grams of O2 in that context? So grams of O2 would simply be whatever you're given times 32 grams per mole. 0.00287 mole O2 times 32 grams per mole O2, and grams O2 if you have to put it in there. Those cancel. Until you can work with sig figs or however you want to do it in the problem that you're dealing with. Now, this needs to be as familiar as your name. Okay? With rhetorical. If I ask you your name, you don't have to think about it. You just tell me. That's the way I'm suggesting you learn this. So, what I would put here in conclusion, so to speak, is grams to moles divide by formula weight. If you're going from moles to grams, multiply by formula weight. And get used to that to the point where you can do it instantly. You'll know what to do. Now, you may have to use your calculator, but at least you know what to do to make those conversions. So you're given copper sulfate at 5H2O. That's copper sulfate pentahydrate. The dot means you have 5 molecules of water coordinated. So if we wanted to calculate the percent water in this formula, we'd determine the formula weight of the copper sulfate pentahydrate, formula weight of 5 H2Os, and take the ratio of H2O to the copper sulfate times 100. So formula weight, of course, involves a copper plus a sulfur plus 4 oxys plus 5 H2Os. And copper, 64, grams per mole, 32 for sulfur, 4 times 16 for oxygen, and water is 18, 116 plus 2. So that's 5 times 16. And we'll tag that grams per mole. I think that's 2. Okay, then of course we need the formula weight of 5 H2Os is 5 times 18 grams per mole, and that gives you 90 grams, well actually just 90 grams for the 5 moles of water. Now the units are going to cancel out of this anyway, because in percentages it's mass over mass, and there will cancel. So we have 90 grams over 250 grams times 100% grams, of course, and I believe that's 36%, and that's a weight ratio. So that's what I wanted to just put in your notes so that you would see that, and all of them are calculated in the same context. You pick out the total number of elements, masses, divided by the formula weight of the compound, times 100, and you get percent composition. Okay. Okay. May have mentioned this in the past. Empirical formula by definition, smallest whole number ratio of elements in a compound. And molecular formula is the actual number of elements in a molecular compound. Now, problems will come to you in two formats, where the data is given in grams of a compound and one of the elements mass, and you work from there. Or it's going to come to you in percentages per hundredweight. And the object is to start with percent per hundredweight. If you do that, then I'll show you the sequence that you'll have to follow, and after you see me work through one, I think you'll appreciate how simple it really is in the setup. Percent to grams to moles to ratio. I'll explain all of this. Reduce empirical ratio and empirical formula. So that is the calculation sequence, starting with percent per hundredweight. Now, this leads to the empirical formula. Now, for a molecular formula, there's a relationship between molecular weight and the empirical formula weight, and it's called a whole number multiple of the empirical weight. So we write this in a simple formula. It says empirical formula weight times n, and that is the whole number multiple is equal to the molecular weight of whatever compound. Now, typically in a problem, the problem will have to give you that molecular weight. And after you calculate the empirical formula, then you can get the empirical formula weight out of that empirical formula. Okay. Get this, this is one of each type. One starts with percent per hundredweight, and the second one you'll notice how it's listed with mass numbers in the problem. In this first problem, it reads, we'll put it up here, what is the empirical formula of a substance that's 56.6% potassium, 8.68% carbon, and 34.7% oxygen? Well, what you have is percent per hundredweight values. Now, the way I suggest you set this up in practice, and there's plenty of opportunities in this handout, is start by listing over here on the left the order potassium, carbon, and oxygen. Put K, C, and O. You might put it in percent like this. And potassium is 56.6% by weight, and 8.68% for the carbon, and 34.7% for the oxygen. Now, up here on the top, we're going to go, I'm just going to put a little percentage right here, and then I'm going to put an arrow, and then we're going to go to grams, like that. Now, how do you go to grams? You just drop the percent and put a G on it, like this. 56.6 grams, 8.68 grams, and 34.7 grams. How easy that was? Now, what's the rationale here? If you add these percentages that are given in the problem, you will get 100%, right? So if you have 100% of a compound, how many grams of potassium would you have in 100 grams? Oops. You have 100, if you add these up, you have 100 grams of compound. If 56.6% of the 100 grams is potassium, how many grams would you have? 56.6, and that's the rationale. See what I did? Just drop the G percent and put a G on it. Because if you start with percent per hundredweight, it's just drop the percentage and go to grams. Now, the next step in here is moles. I'm going to move that over just a little. Right here. Well, how do I go to moles? Given grams. If you look back in your notes, it's divide by formula weight. And get used to that. Grams to moles, divide by formula weight. Grams to moles, divide by formula weight, etc. So we want to look up, and I just put a slash mark right there. And I look up, well, I know what carbon is, I know what oxygen is. 39 is the potassium. And that's, of course, grams per mole. And so I'll have the moles of each one of these elements. 56.6 divided by 39 is 1.45. I suggest carrying out 3 or 4 decimals at this point. 1.45123. 8.68 divided by 12 is 7233. And 34.7 divided by 16, 2.1687 or 88. Everybody still with me? Okay, now the next step is you set up a ratio. Okay, that is your potassium to carbon to oxygen ratio. And I skip down under all the initial calculations like this. And if I have three elements in my compound, then I want to do this: blank, colon, blank, colon, blank. Do that. Now, the ratio refers to the mole ratio, so I'll put the mole ratio on top. And that will be 1.4513, 0.7233, and 2.1688. Okay, now at the bottom you want to reduce by dividing by the smallest of the number set that you just had. Divide by the smallest number. And so if you look at your collection, the smallest number in this, 0.7233, 0.7233, and 0.7233. So what this gives you is the empirical ratio. And we see that 1.4513 divided by 0.7233, and that gives me a 2. And that one's obviously 1, and then the last one, 2.1688 divided by 0.7233, and that gives me a 3. So this is your empirical ratio. Therefore, your empirical formula is K2CO3. And that's how that's done. We go percent to grams to moles, then we set up our ratio, and then we reduce the ratio to get the empirical formula. And then that shows the way we do it. And so what you need to be sure you understand is this: percent to grams to moles to a ratio, reduce, that's divided by the smaller number, and that gives you your empirical ratio, which leads you to the empirical formula. Simple as that. Now, in this problem, we were given percent per hundredweight, right? So the second problem is giving you in mass values. So what you need to do first is convert to percent per hundredweight. And it's nothing more than percent composition based on the numbers given, and then you follow the same percent to grams to moles ratio, reduce, and empirical formula. Okay, in this next problem, we read, what is the empirical formula of a compound composed of 3.26 grams of arsenic and 1.04 grams of oxygen? Well, they give you the individual elements. Well, you add those together to get the total mass of the compound. Okay, so in this problem, we're given mass of arsenic is equal to 3.26 grams, and the mass of oxy is 1.04 grams, and we add those together in mass of arsenic oxide or compound is equal to 4.30 grams based on the data given. Well, I need from here, what's the percent hundredweight of arsenic, and what is the percent hundredweight of oxy in here? Well, how do you get that? Well, the percent of arsenic is 3.26 part over the mass of the the compound, times 100%. Now, when you get that one, you can get the percent by weight of oxy simply by taking 100% minus the percent of arsenic from the first calculation, like that. Or you can do the ratio either way. Now, if you have 3 components, you'll have to do at least 2 of these, and by ratio, and then you can add them up, subtract from 100. So this one is 75.81% by weight. And then subtract that from 100, and I get 24.19% weight. And so now we can go with the percent to grams to moles to ratio, reduce, and get our empirical ratio. And of course the empirical formula. So in the same way that we did the last problem, we'll take the percent arsenic and the percent oxygen, put those down first, drop the percentage and tag it with grams, and then divide by formula weight. Oxygen we know is 16. I have no idea what arsenic is. Arsenide. 75. So I think it is 1.011 mole of arsenic and 1.273 mole of the oxy. And so since we have just 2 elements in our formula, we want the ratio of arsenic to oxide. We put 2 blanks like this, and we take the moles and put them on top, and divide by the smaller of the 2 numbers. Okay, we made the correction here on the oxygen. Sorry about that. Anyway, it reduces, of course, to 1 to whatever that one comes out to be, and that's divided by 1.011, and that's 1.5. Now, this is a unique situation right here. Now, if one of the ratios in your calculation comes out the following: 1.25, 1.5, and 1.75. Now, you won't have anything in between all of that on test day. This says you have the right to multiply by 2. So times 2, and your empirical ratio is 2 to 3, and that's your empirical formula. Arsenic, yes, AS, I'm sorry guys. That's argon. Arsenic is that. So it's arsenic oxide would be, and there's your empirical formula, like that. If ratio contains whatever 1.25, say dot whatever 1.25 or 1.50 or 1.75, then what you should do to that number, this one is times 4 times 2 or times 4, like that. So if your ratio is 2 to 1.25, then you multiply everything by 4, because 4 times that will take it to the whole number. 2 times that will, of course, take it to 3, and 4 times that will take it to 7, I think it is. So these are little memory things that you have to take with you into that empirical formula calculation, such that if the ratio comes out containing one of those, you know to multiply to, you have the right to scale it up to the whole number. Now here is a problem which asks you to determine the molecular formula, and it reads, an unknown compound is analyzed and found to consist of 24.3% carbon, 4.1% hydrogen, and 71.6% chlorine. If the molecular mass is 98.8, what's the molecular formula? So you have to first calculate the empirical formula using the procedure I just showed you, and then apply the empirical weight times the whole number multiple n equals molecular weight, which they give you in the problem, and find out what that n is, and then you subscript multiply the whole number multiple into the empirical formula to get the molecular formula. So in this problem, first get the empirical formula, and we're looking at carbon, hydrogen, and chlorine. .3, 4.1, and 71.6. And so going to grams, we drop the percentage. And then divide by formula weights. And we'll get the moles. And so since we have 3 components, we need 3 lines and a colon, line, colon, line, colon. We put the moles on top. And we divide by the smaller of the set. And of course that gives us the empirical ratio. Okay. So we're looking at an empirical ratio of 1 to 2 to 1. So the empirical formula is carbon, hydrogen, and chlorine. Well, the empirical formula weight now is carbon plus 2 hydrogens plus a chlorine, which is 12 plus 2 times 1 plus 35, 45, 47, 49. 9 grams per empirical formula weight. And so the mole weight given n times the empirical weight. And so our object is to get that whole number multiple and then distribute it through the empirical formula. So it's given 98.8, isn't it? 98.8 grams per mole. You don't even worry about units because all you're looking for is the n number divided by 49, and n is equal to 98.8 over 49. And it looks like a 2. So there's your whole number multiple, and you take the 2 and distribute it through the empirical formula, and you get your molecular formula is now C2H4Cl2. So you distribute that whole number multiple through that formula. Okay, this is the 3 types of problems you will see on test day. Either it's coming to you in percent per hundred weights or grams, so you know to convert to grams to percent per hundred weight, and then follow the sequence. And you need to remember, of course, this relationship between mole weight and empirical weight, so you can scale it up to whatever you need. And don't forget the 1.25 thing and 1.5 and 1.75 thing.